So in this section, we're going to talk about a few of the applications of the definite integral. These are by no means all of them, it's just the few that were picked for this textbook. So the first one is average value of a function. Now the average value of a function, f of x over the integral from a to b, is going to be defined as 1 over b minus a times the integral from a to b f of x dx. This of course makes more sense if we try an example. So let's see, in 1998, they estimated the world population in billions of people would follow this formula. P of t is 5.9 e to the 0.134 t. So this is a nice growth, exponential growth formula. And we want to know what's the average world population from 98 to 2018. This is of course a very important question that would have lots of implications for anyone that's governments are trying to plan, things like that. And you can kind of see how it makes sense to say, okay, what's kind of our average here? So our average is going to be 1 over, okay, we need to know what b and a is. Now when they say from 1998 to 2018, this was kind of starting at 1998, and so this is going to be t equals 0. In 2018, that's a difference of 20 years, so this is going to be t equals 20. So we're going to go 1 over 20 minus 0, and then we're going to integrate from 0 to 20, our 5.9 e to the 0.134 t dt. So this 1 over 20 stays out there. The 5.9 just gets to stay there as well. Now e to the 0.134 is going to stay as e to the 0.134 t, that stays. But then I have to do 1 over this number in front of the t. So 1 over 0.134, that's a times. Evaluated from t equals 0 to 20. So let's simplify. 1 over 20 times 5.9 divided by 0.134. So I get 2.2 e to the 0.134 t evaluated from t equals 0 to 20. So we plug in our top limit first, 2.2 e to the 0.134 times 20 minus 2.2 e to the 0.134 times 0 should give me 29.9. So again, if you want to find the average of something, you would integrate from your limits, and on the outside you'll do 1 over the b minus a. And so our final answers, they were predicting, this is back in 98, I'm sure they revised their prediction, they predict that the average world population from 98 to 2018 in billions would be 29.9 billion. So that's going to be a lot. We'll see what their new revision is. Now, consumer surplus. Okay, so this is a business application. Consumer surplus is the difference between the maximum amount that consumers are going to say they're willing to pay and the amount that they actually do pay. Okay. So the demand curve, that's kind of our theoretical, or what we're kind of like willing to pay. Or it's the price that you need to set to sell X goods. So if the person knows they want to sell 1,000 books, what price do they need to set? What price are people willing to pay so that they can sell 1,000 of them? Now, we're going to define A as the quantity sold, our actual X value, that how many we sold, and B equals f of A. If you just plug A into our price function, what is the actual price for the actual quantity sold? And so this is what we actually pay. I just realized I typed this up and I don't have any limits on my integral. You actually integrate from 0 to a. Okay. So now let's find the consumer surplus for our demand curve. This is kind of our f of x or p. Usually we call it a p or even sometimes a q in this textbook. And we want to do it at the actual level of 30. So let's set a few things up. According to my formula, my f of x is going to be this 100 minus 0.07x squared. My actual x level, or my quantity sold, A, is going to be 30. And B, which equals f of A, in our case is going to be 100 minus 0.07 times 30 squared. Or 37. So now with all of that, we can go ahead and set up our integral. So we need to integrate from 0 to a, which is 30. We need our f of x, so 100 minus 0.07 x squared, minus b, and b is 37, dx. At this point, I'm just going to skip to the answer, and you can try all of the actual integrating on your own. Or 1260. So this kind of tells us if the publisher wants to sell 30 books and they actually sold 30 books at a price of 37 each, they probably lost out, or the consumers probably about saved total overall $1,200 based on what the consumers might have been willing to pay and what they were actually charging. This one is interesting. It's called future value of an income stream. So let's say we have a bank account that has money coming in continuously throughout the year. Okay, and the interest is compounded continuously. So again, we put this in a bank account, interest is compounded continuously, but I'm not just putting money in once, I'm putting money in continuously. So what we can do is we can find the total amount that we would have after a few years. So what we're going to do is K would be the amount of money deposited each year. Again, we're not depositing it just once, we're depositing it. So this K, like say it's $1,000, is being broken up into small chunks and put in several times a day or 10 times a day throughout the entire year. N is the number of years we're interested in, and R is our interest rate. So our future value, the amount we'll have after so long, is going to be from 0 to N, K, the amount we deposited each year, E to the R, and then we'll do N, the number of years we're interested in, minus T, and T is my variable so I can integrate. So let's do our example. Suppose we deposit money several times a day into an account that's compounded continuously. So because we're depositing money several times a day, we'll say that's like the money coming in continuously, is compounded continuously. We deposit $2,000 a year, so that's our K. Okay. N is our number of years we're interested in how much money is in the account after 5 years. And the account pays 3% interest, so R equals 0.03. Now you'll notice the examples that we've done in this chapter have a lot of kind of complicated formulas. I'm not expecting you to memorize all these formulas. That's not what I expect in a math class. I expect that if I give you the story problem, then you can figure out, okay, which kind of thing was this, and then use the formula that you have written down. So our future value in 5 years, how much money will be in there? So I keep putting the money in continuously. It keeps compounding it continuously, so we have interest to deal with. So we're going from 0 to 5, N is 5. K is 2,000. E to the 0.03 times N, which is 5, minus T, dt. And let's see, we might need a little bit of help to integrate, so this one we actually will work out. So we're doing the integral from 0 to 5. Let's simplify a little bit. This is 2,000. E, let's do 0.03 times 5 is 0.15 minus 0.03 T dt. Now, when you look at this, have you ever integrated something exactly like this before? Probably not, and we haven't actually learned formulas that would let us do that, but what we can do is say, use our exponential rules. So this is really like from 0 to 5 of 2,000 times e to the 0.15 times e to the negative 0.03 t dt, right? Our exponential rules say if you're timesing two exponentials, you could just add their exponents. Now this entire thing is just going to be a constant, or a coefficient if you prefer. And so that entire thing, e to the 0.15, that's just a number. That's not a variable anymore. I can pull all of that out of my integral. So that's 2,000 e to the 0.15 times the integral from 0 to 5, e to the negative 0.03 dt. And at this point, you know how to integrate that. So if I integrate it all, I'm still going to have this 2,000 e to the 0.15 times, now e to the negative 0.03, let's go down, I never have enough room. So my 2,000 e to the 0.15 is still here. Now when I integrate, e to the negative 0.03 will stay e to the negative 0.03, but then I have to times it by 1 over negative 0.03. And I'm going to evaluate this from 0 to 5. Oh, sorry, I dropped off my t. So let's pull all of my constants out. E to the negative 0.03 t evaluated from t equals 0 to 5. You don't have to pull all your constants out, but then you don't have to write quite as much when you evaluate it. So my 2,000 e to the 0.15 over negative 0.03 is going to be times e to the negative 0.03 times 5 minus e to the negative 0.03 times 0. All of this gives 10,788.95.